So, fourth test on DC machines one is Hopkinson's test. Hopkinson's test on DC machines test. So, this test having different names. That is, this test has back-to-back test and heat run test and different names it has. It is in the all the tests which are performed on DC machines, we have to take lot of precautions and lot of concentration is required here. Understand? So in this test, the another important point here in this test, we require two machines. One is DC motor, another one is DC generator. But here we are using shunt, DC shunt motor and DC shunt generator. Both are identical. Both are identical. Right. The another name, this is the full load test because we are operating at the full load. We are operating at this test is full load test. What is the no load test? No load test is the swing bus test. This is the load test actually. Right. So, but by using that two motor and generator, we calculate both efficiency of motor and generator. Both machines we will calculate. Right. This is the apparatus. This is the nameplate details. Just observe here. In this, look at here. We have one DC shunt motor. That's why this is the field is in shunt panel. And we are using the another identical machine, that is DC shunt generator. That's why we have the here we have a rheostat. For that we are using the shunt only. And the motor coupled to the generator. So this motor required mechanical power will given by this motor to this generator. And before connecting the motor and generator, we are connecting a SPST switch, single pole single through switch. So the single pole single through switch before just keep open before starting the experiment. That's why this is the motor shunt connection. And to find out the input voltage to the motor, we are connecting the voltmeter. To find out the input current to the motor, we are using the ammeter. And we are giving the supply from the DPST supply 220 volts, and we are using the DPST switch, and a fuse is connected here. And for that generator will take the input power from this motor, and in order to find out the voltage across the generator, we are using a voltmeter here. And in order to find out the current across this field, we are using a ammeter here. We have ammeters. Motor having the ammeters are two. One is for low line, one is for field, and we have the voltage across the motor. Generator also, and we have the another voltmeter across the switch. And generator also having the two ammeters. One is for field, another one is for supplying the load. Here, right? Look at it. So same procedure for this to measure the armature resistance. So the procedure is before starting the experiment, just look at the rheostats of the motor, shunt motor, rheostats of the shunt generator. For the shunt motor, just keep the motor rheostat is minimum position and keep the generator is the maximum position. Look at here. This is the maximum position and this is the minimum position. This is the fixed variable, this is the fixed point, this is the variable point. And look at here, this is the fixed point, this is the variable point. Right. So initially start the experiment varying the field rheostat, just keep the motor at the rated speed. It has a 1500 speed, you know that. It has a 1500 speed, just keep that at the 1500 speed. Just keep the 1500 speed by varying the field restart. Varying the field restart. Right. Then generator will generator also generate the some power across this. That power will be supplied to this field. This power will be supplied to this field, and this is the open, and this is the open. Just by varying this field, just by varying this field, observe the voltage across this. By varying this field, wherever the voltage across the switch is zero, just close the switch. Just close the switch. That means the same voltage, supply voltage and generator voltage must be same. That's why this shows the zero. That means for the motor it acts as the no load. For the generator it will act as no, it generator also acts as no load. Understand? Motor is at no load condition, generator is also at no load condition. So motor has load condition, generator is at the no load condition. Right. Again, by varying the field, simply by varying the field and by applying some field, generator voltage will be increases. Generator voltage will be increases, the automatically this current will be flow into some motor and some of the current will be entering into this field. Again, by varying the field, automatically generated EMF value increases again. That will be supply current to this motor and supply to this field. That's why I observe here. Look at here. First, tabular column input voltage, never change the input voltage, and total input taken from the load by the motor is 3 amps only. Generator field, look at the generator here. Initially generator is 0.5. By varying this 0.55, by varying the 0.57, that means by varying this generated voltage across will increases. Generated voltage is increases. Understand? So there is no tablet column actually, but we can understand. That means generated voltage will supply the power. That's why generator output current 1 amp, 1.5, 2.5, 3 and 3.5 increases. But input power from the motor, there is no change in input power because motor will take only that power only. Understand? Input power, right? But armature copper losses of the motor, by increasing that here, by increasing this generator, automatically the more amount of current will be supplied to this, the generated mechanical power will be again supplied to the generator. So both are both are acting as generator and loads. So motor is gives mechanical power to the generator and generator will supply the electrical power to the motor. So these two can be operated. That's why here, observe here, although the armature current, the line current from the supply is same, but the loss will be increases. Look at here, 19, 26, 41. The reason is generated voltage is increased across the generator. Then armature copper loss of the generator also increases because generator generates more power. And motor field copper losses are constant. The reason is motor field, the generated power from the generator only supplied to the armature only, not for motor. And generator field losses also increases because look at here, whenever it generates the more current, some of the current will be supplied to the motor and some of the current will again supply to the generator because it has to supply, right? Okay, that's why this also increases. The stray load losses, that from the total input power, the removing the all the losses, total input power from no load condition, we will get the stray load losses here. Total losses of the motor, copper losses and stray load losses by 2. So we will get the total losses. and total losses of the generator. So by using that we will get total losses. So efficiency of the generator. Efficiency of the generator, input to the output of the generator and input of the generator. Output of the generator is, this is the generator output current and the generator voltage. Output current and generator voltage, right? This will be increases. So efficiency of the motor. This is the efficiency of the motor. Here generator efficiency 43%, 57%, 52%, 60%, 65%, 16%, 16%, 72%, 73%, 74%. What is the reason efficiency of the motor is increases? The motor will take the power from the generator. Understand? This is about the Hopkinson test. This is about the calculations. These are the calculations. Just go through these calculations. You will understand each and everything. And before that, just look at the diagram very clearly. Understand? Yes, this is about the Hopkinson's test. So once again, the Hopkinson's test named as back-to-back test. The reason is motor output is connected to the generator and generator output is connected to the motor. Back-to-back test and full load test. Here the motor is operated full load and generator is also operated at full load. That's why full load test. And this is the heat run test. So heat run in the losses heat. So that's why this is the heat run test. Right? Okay. This is about the Hopkinson test. This is very, very important test. And very, very important test. Okay. So the first you need to know, in order to understand very clear, first you need to do the basic operation of the motor and generator both. Motor and generator both. Okay. Right. Thank you.
Hello students, today we need to discuss about the Hopkinson test. So this Hopkinson test we need to perform on shunt MG set, right? So already we have discussed about the field test. That field test will be performed on series MG set, but the generator output should not be fed to the motor side. But coming to the Hopkinson test, the generator output should be fed back to the motor side, right? So that is the advantage. So here by performing Hopkinson test, we have to determine efficiency of shunt motor and shunt generator at a time, right? So actually what we are doing, it is a shunt motor, right? So we are familiar with the shunt motor operation. It should be run with the help of 3-point starter, right? So it consists of 3 terminals, L for line, A for armature, F for field. So what I am doing, directly I am giving line to positive, right? If you want to, here I want to measure the supply current, right? So total input current, how much current is flowing through the combination of your shunt MG set. So for that purpose, line to ammeter positive and ammeter negative to positive supply, right? Next, for the motor field winding, I am placing one rheostat in series with one ammeter, right? So this is your motor field rheostat from field to here, and finishing terminal of your rheostat should be connected to the ammeter positive, right? Next, ammeter negative should be connected to the double F. Next, double A to double F, double F to negative supply. So as usual, the shunt motor connection, right? Now after completion of the shunt motor connection, so what we need to do means, first of all, after giving the connections, we need to turn on the MCB and we need to apply slowly the 3-point starter. Then we need to vary or we need to adjust the field rheostat of the motor in such a way that the motor speed has to attain the rated speed, that is 1500 RPM, right? After completion of that, then we need to give the connections of your generator, right? It is a shunt type, so armature and field both are connected in parallel, but I want to measure generator output current, right, as well as the generator armature current and the generator armature voltage. So before switch on the generator side, so what we need to do, we need to connect one switch, right? We need to connect one switch in series with your armature, and across the switch we have to place one voltmeter. Across the switch we have to place one voltmeter. So this is the voltmeter I am placing across the switch, right? So what we need to do, after adjusting motor as to a rated speed, after adjusting motor speed as a rated speed, what we need to do, slowly we need to vary the generator rheostat, right? Slowly we need to vary the generator rheostat in such a way that across the switch we have connected one voltmeter that has to display only 0. Initially it may come 20 volts, 30 volts. So up to 0 volts we need to vary the generator rheostat. Then we need to close the switch connected in series with the armature, right? Then we need to observe the generator output current, right? So this is our generator output current and this is your generator field current and this is the armature voltage. So here in this experiment we need to observe total 4 currents and 2 voltages, right? So what are the 4 currents? First one is total input current. For the combination, how much current we are pumping, how much current we are inserting, right? With the help of supply. And next, this is the motor field current, right? This ammeter will display motor field current. And what about this I3? This ammeter will display generator output, which fed back to the motor side, right? And next, coming here, I am using this multimeter as an ammeter. So this ammeter will use the generator field current, and this voltmeter is your motor voltage or the supply voltage, and coming to this voltage across the armature of a DC generator. So after observing all the meters readings, then what we need to do? We need to calculate motor and generator field and armature copper losses separately. After that we need to find the stray losses. So combining these losses, field copper losses, armature copper losses, as well as the stray losses, we need to find the total losses. So by using the total losses data as well as these meter readings, right, we need to find the efficiency of DC shunt motor and DC generator separately at a time. So this is the advantage of the Hopkinson test. Thank you. So today our experiment is Hopkinson test. So already we have performed field test, right? So what is the drawback of the field test? Whatever the generator output we are getting, that output is going to be wasted, right, through the load band. So that output here we are giving or we are feedbacking towards the motor side. Means the output of the generator should not be wasted, right? That also we are utilizing towards the motor side. So that is the advantage of the Hopkinson test. And this should be performed shunt MG side, means shunt motor and shunt generator coupled side, right? We have to perform the Hopkinson test on the shunt MG side type. So here, if you want to find the shunt motor efficiency as well as the shunt generator efficiency at a time, with the help of Hopkinson test we are able to find. So already we have given the conditions as per the circuit diagram. So let us operate the Hopkinson test, right? In order to determine the efficiency of the DC shunt motor as well as the DC shunt generator. So I am going to power on for your Hopkinson test, right? And next it is a shunt motor. So we need a 3-point starter, LAF. So with the help of 3-point starter, we need to start your DC shunt motor, right? So after giving supply to the DC shunt motor, by varying the field rheostat of the shunt motor, we need to adjust up to the rated speed 1500 RPM, right? So after setting the speed of the shunt motor at rated speed 1500 RPM, so if you observe here, this multimeter is acting as a voltmeter. We have connected across the switch, right? So this multimeter has to show the 0 voltage, right? Then only we need to close the switch. So we need to get this voltmeter as a 0. So by varying the field rheostat of your generator, we need to obtain the voltmeter reading should be 0. So up to that point we need to vary the field rheostat, right? So if you observe slowly it is decreasing, right? So 1.0, 0.1. So now if you observe it is a 0, right? Nearly 0. So after getting the 0, we need to close the switch. So if you observe this ammeter, right? So if you observe the generator output, initially it should be 0. Now it is deflecting, right? So by varying the field rheostat of your generator, if you observe the ammeter, right? Slowly it is increasing. So in this experiment, we need to focus on these 5 meters, right? So what is the first ammeter? It is the motor field current, right? And next first voltmeter is motor voltage, and second ammeter is generator, right? Generator field current, and next one is generator voltage, and next one is generator output current, right? So generator output current this ammeter, and generator field current will be this ammeter, right? So with the help of this I1, I2, I3 and I4 as well as V1, V2, what we need to do? We have to find the copper losses, right? Copper losses of your motor as well as the copper losses of the generator separately. So from that data, we need to find the efficiency of the DC shunt motor and DC shunt generator, because the motor input is simply the product of the voltage and current. So that is nothing but your generator output. So you have the data, motor input as well as the generator output. And by performing this experiment, we are getting the field copper losses, armature copper losses of both the machines. So if you know the input and losses, then we are able to get the output. By combining those data, we are able to find the efficiency of the DC shunt motor and DC shunt generator. After that, we need to draw the performance characteristics. Now what we need to do? So we need to open the switch, right? Then slowly we have to vary the field rheostat in such a way that the meter has to show the zero reading again, right? So it should be 0. Then turn off the MC. Turn off the MC. Thank you.